Okay, hi everybody. For those that they don't know me, I think it's just one. I'm Athanasios Vourvopoulos, aka Thanos. I'm a PhD student here at MITI, and I will present a pilot study with some preliminary results from my independent study, which is not directly connected with my PhD topic, but it has some overlaps. This study is entitled "The Effect of Prior Gaming Experience in Motor Imaginary Training for Brain-Computer Interfaces." Many of the terms maybe you're not familiar, like motor imaginary or brain-computer interfaces. So I will slowly introduce you and explain the relationship between the two, and also the relationship between games, used games, and the brain. Initially, so far we've been able to see that people that are regularly exposed to video games have improved visual spatial attention, memory, mental rotation abilities, and they have enhanced sensory motor learning. Furthermore, people that they have extensive video game practice have also been shown to have improved efficiency and movement control on brain networks and visual motor skills. So, what that means. Basically, mental rotation, motor imaginary, and for example, remembering familiar faces and all the mental tasks that I explained before are really important for brain-computer interface interaction and training. And really simply, it's because brain-computer interfaces are simple communication systems which translate brain activity into control signals. We get this through specified algorithms. We get this control signal, and we can give it as an input either in a computer or an external device like a robotic hand or a prosthetic. Now this is part of a loop, which is called it's a neurofeedback loop, a closed loop, and it starts from the user, where the user initially on a motor imaginary brain-computer interface has to simply perform a mental practice and just to think of motor action only by performing this by thought. And there is a certain brain activity and patterns created on a specific part of the brain, which we're going to see later on. And this electrical activity, we can capture it with some invasive or non-invasive electrodes. In this case, obviously, it's non-invasive. And we can translate this electrical activity to we have to do some processing on a computer level. We filter the signals, and then we classify the signals based on the brain activity of the user, based on intention. After this processing on a computer level, we're able to get a control signal, which is the output of all of this processing. In the case of motor imaginary, we can get an output like left-hand movement or right-hand movement as identified by the computer, and we can input this type of data either to a game, a virtual environment, or a robotic device. And then the loop is closed by the user getting the feedback of this triggered action, and so on and so forth. Now, how this works actually is really interesting, because motor imaginary is relating on the same brain systems that are used when we actually perform the same task. On the right-hand side, you can see some of the cortical activations here of the brain, while the participant is performing the movement. And on the right-hand side, you can see almost the same activations on the brain, on the same area, and similar intensity, when the user is actually thinking of the same action without performing it. So as you can see, this is a really important aspect, motor imaginary, and through this methodology, we try to capture this activity and translate it to the computer. Now, one of the latest trends, especially in the gaming domain, is the neurogaming. It's the brain-controlled virtual environments, which main input is the brain-computer interface, and obviously this excludes traditional controllers like a mouse, keyboard, or other natural user interfaces like Kinect, Wii, etc. So a pure brain-controlled game, it only uses a BCI as an input, not hybrid devices, hybrid systems that we have so far with a large amount of inputs from different devices. Now, brain-controlled games are not it's not a simple case. It's not something simple to design and to perform. So based on this complexity, there's a big set of limitations because users need to go through a long and repetitive training trials, which is really cognitively demanding and really huge training, which results in user fatigue, and we see a declining performance over time. This is really bad, especially if you want to enhance the engagement on the task, the brain control task. Now, so far we don't have also a clear relationship between video game practice and brain-computer interface training. So current neuro games in brain-controlled virtual environments, they don't take, they don't actually know what is the impact of the and experience of the gamer that is actually using his brain input into the brain-controlled games. So this is a big gap. Now, in this study, in this pilot, we started by assessing the neurophysiological correlates of previous gaming experience and how this experience is reflected on a motor imaginary training. For this, we created an experimental setup, which included a standardized BCI training paradigm. So we didn't create any training from the beginning. We used a standardized trial, which you're going to see later on. And we tried to divide the two different user groups based on their previous gaming experience through a classification method we're going to see later on. In this study, the type of acquired data involved subjective responses through questionnaires, demographics through population data. We got electrophysiological data and the EEG rhythms, as we're going to see later on. And finally, we got the training score based on the classification percentage that we get from the computer. Now, for this study, we started with 12 participants, a mean age of 28 years old, 8 male, 4 female, and one of the participants was left-handed. For acquiring the brain activity, we used a simple EEG cap with some active electrodes, and these are touched over the scalp with some specific gel, so we can get the electrical activity from the scalp of the user. And we placed some electrodes, 8 electrodes, over the motor cortex and somatosensory cortex of the brain, which these areas are responsible for motor action, motor movement, and motor imaginary, as we saw previously. Starting from frontal central electrodes, then we cover the central area and the central parietal area. And then we have one set of electrodes on each hemisphere of the brain. Now, for displaying the feedback during training, we've used the simple VR head-mounted display, which it has two LCD displays, and it's not very immersive. It's not like an Oculus Rift, but it serves a purpose because we didn't want to use just an external monitor with people having external stimulation and visual stimulation from other sources. We just want to narrow it within the task, and this head-mounted display seems to do the job. And it looks through this display, you can see it feels like you're watching a 44-inch TV through a distance of 2.7 meters, which is around 9 feet. Furthermore, the training task, which is a quite standardized task in the field, it's the Graz visualization task from Graz, Austria. And this task starts with, I don't know if you can see, it's a fixation cross, where it prepares the user for 1.5 seconds, and then consequently we have a cue of an arrow, directional arrow, either left or right, for 3.75 seconds. That cues the user to perform motor imaginary based on the direction of the arrow. It's going to have a motor imaginary of the hand, left or right, based on the direction. This loop is performed 20 times per hand, 20 for left, 20 for right, in a randomized order. in order to acquire all the necessary data to train the algorithm, to train the computer to differentiate between the two classes, between left and right. Now, the questionnaires that we used for this study included the Edinburgh Handedness Inventory, which is a questionnaire to classify handedness. So it's not just it has a higher resolution than just simple left and right handedness as reported by the user. So for left-handed, we can have a spectrum between minus 100 to minus 40%. And for right-handed, it's between 40 and 100%, and all in between for ambidextrous. So there's many people that they say that they're right-handed, but in principle, they might be ambidextrous or not as right-handed as other people. So it's really important to have this spectrum and classify handedness. Moreover, we use the Vividness of Movement Imaginary questionnaire, in specific the kinesthetic imaginary part, which in this questionnaire the user has to report his ability of his ability to have vivid images of some mental imaginary. For example, if they have a clear imaginary of moving their hands or their feet, so we can classify between 1 to 5 on a Likert scale. If they have a clear sensation of themselves moving, only by movement imaginary. So if they feel comfortable by thinking themselves walking, throwing a stone, or kicking a stone, so we can classify this abilities through this questionnaire. Moreover, we use the game addiction questionnaire, which we try to classify between low, moderate, high, and very high. It scores between 0 and 80. It's a modified game addiction questionnaire. And finally, we use the gamer dedication questionnaire that we try to classify gamers based on their previous experience. For non-gamers, casual, transitional, hardcore, and ultra hardcore. Now, for grouping the players, we use the gamer dedication questionnaire, which we try to, through this formula, we try to classify the two groups. We got the scores and we'll multiply it based on a weight given through this formula and through this classification. And we ended up classifying two groups. One is the hardcore group and the other is the moderate group. And now that we have this type of groups, we wanted to extract the EEG rhythms. And what are the EEG rhythms actually? And what is this brain activity? So basically we took the raw EEG signal, and as you can see, this is not just brain activity. For example, this part here, it's probably an artifact that is it's generated through eye movement. So so there's a huge amount of components that they form one signal. So we want to take the signal, clear it up, and having finally an end product that could more or less be relevant to brain activity. So we tried to do some filtering on the signals. We threw away some ECG, EMG signals. We had some noise from power line noise. And we tried to get as clear signal as possible in order to extract then a 4 set of bands based on frequency. So namely, we have the alpha band on between 7 and 14 hertz, beta band between 15 and 30 hertz, the theta band between 4 and 7, and finally the gamma band between 30 and 100 hertz. Just to give you a brief idea on what these bands are for, based on current literature, we know that alpha is mostly linked and related to drowsiness, concentration, visual fixation, and sensory motor rhythms. On the beta rhythm is mostly linked to active thinking, active attention, and again, sensory motor rhythms as alpha. Theta is more linked to meditative, relaxed, and creative states. And finally, gamma is more closely linked between visual, auditory, somatic, and olfactory perception, and also attention. Now, results. So, step number one, we wanted to see how can different groups modulate their EEG patterns based on those bands that I mentioned. So what we did, we tried to see, we took the first and the last session. The users had 3 sessions within 1 week. So we took the first and the last and wanted to see how is the EEG patterns behaving. For the alpha band, we've seen that there is a huge difference for the hardcore group, which is right here. So the hardcore group had almost 7.7% increase of alpha in the end of the sessions, and the moderate group had the decreased alpha activity, 4.7%. For beta, the decrease of the hardcore group was small, around 1%, and we had bigger decrease of beta on the moderate group on 3.66%. Now on the theta, we see again increase of 3.7% on the hardcore group, and moderate group had around decreased 3.4%. And finally, gamma is the only band that hardcore group here has less difference in activation than actually the moderate players. So as far as you can see, there's quite of a difference between the two clusters of groups, and overall the difference between the hardcore and the moderate, we see that on the alpha band there's a difference of 12%, beta 2.6, theta 7, and on gamma there's less activity of around -3%. Now these results are projected into the training aspect and the training performance of the participants. Here we have a box plot of the difference between the first training session and the last training session. The result of the training session is given by a percentage, and that's the percentage of how well the algorithm can detect between left and right hand movement, so how accurate it is. And so far we see that on the same amount of time, on the same time window, we see that the hardcore group was able to increase their performance 3% faster than actually the moderate group 1.5%. So at the same time window, we see that also there's a faster learning. Obviously, there's a learning effect between those trials, but we see that hardcore group, they managed to have better scores, so maybe they're trained faster and more efficiently than the other group. Now, that's just a simple relationship between some demographics and EEG pattern modulation, although there's a small sample to have concrete statistical significances. We've been able to see that we have some gender-related correlations on the beta, theta, and gamma band, and also age-related correlations on the alpha band, that means that we have some higher modulation in women, and some on the beta, theta, and gamma. And for alpha, here we have some high modulation on older people, older groups of people. Now, in order to see the relationship between the subjective reports that we got from the questionnaire and the brain activity, we ran a linear regression model in order to try to map and make a model of the relationship of the two types of data. For alpha, we've been able to see that we have higher alpha modulations based on game journey, as we're going to see later on. People with gamer dedication that discuss games with friends and bulletin boards had also higher alpha. And finally, on game addiction, people that stay up late to play video games had also increased activity. For beta, we had, again, gender-related correlations. And in game addictions, you had people that had unsuccessful reduction of video games duration, people that eat meals while playing, and people that getting headaches, red eyes from playing video games, especially all these elements of game addiction, had some beta higher oscillations. And finally, handedness had also an impact on beta activity. Now for theta, on gamer dedication, people that play games over many log sessions had increased theta. And that's the only relationship that we can find for this band. Now for gamma, on game addiction, active members in activities or clubs had the increased gamma, and finally people with on the kinesthetic imaginary questionnaire that they had high scores on visualizing themselves kicking a stone. They had also high activation of the gamma band. Now to start chewing slowly this kind of data, because obviously there's a big amount of data, there's a small population. We can just draw some simple conclusions, like we've been able to see that gaming experience leading to increased alpha activity can be the reason of that the older participants had higher alpha. That's maybe an assumption that also that older participants had also bigger gaming expertise. So gamers with favored during the action games had also increased alpha activity, which I think this is one of the important elements. And also we've seen that high alpha activity on the hardcore group. Overall, we've seen with past research that there's a correlation between good game performance in the sense of completing a task faster on average with the production of alpha waves. Now for beta activity, we've seen that gamers that unsuccessfully try to reduce the amount of time that they play video games and they had some headaches and red eyes, they had the increased beta activity. Participants with higher level of right-handedness and females also had the increased modulation. And finally, the decrease on the moderate group, but more stable on the hardcore group. Overall, we know that beta is closely related with voluntary movement, and with combination with alpha, over the sensory motor areas of the brain are involved for motor actions. So we know that high levels of addiction also could possibly result into higher sensory motor activation. Now for theta, we see that participants that play games over many long sessions have increased theta modulation during training, and it's increased again in the hardcore group. In theory, we've seen that the cortical theta activity is observed in meditative or relaxing states, but also we've seen this type of modulation in the prefrontal cortex, where it predicts whether people are able to overcome ingrained biases. This is choosing an action that is counter to habit when it's required to achieve a goal. That might be also present because of a training session, and there's many reports by users that they try actually to have some ingrained biases during training. So they try to do an action counter to habit in order to see if actually the algorithm is predicting well left or right. Now finally, for gamma, we see that high addiction players produce higher gamma. It's a bit blurry, the gamma band, but participants with high kinesthetic imaginary related to lower limbs like kicking a stone have increased the activity. And finally, participants of the hardcore group, it's the only band that they had decreased activity over time compared to the moderate group. Now, on gamma, again, it's a bit blurry. We know that the binding of different neurons together, they're used to carry certain cognitive and motor function and oscillating into this type of frequencies. Now, overall, we can see that obviously there's a trend between the two groups. Also, although there's a close relationship in the clustering of the two groups, we can see that there's a strong gaming profile could possibly enhance the ability to use a BCI system. We see differences between all EEG bands. And finally, classification percentages increased performance faster over time for hardcore users. So maybe they learn faster or they perform faster over time based on the classification percentages that we got from the computer. Now finally, we can see that enhanced sensory motor capability of the experienced gamers is partially reflected on this motor imaginary BCI training. Now, how we can use this, there's two sides of these results. We can use these results in order incorporated to neurogaming on the training aspect, so we can stimulate areas that are responsible for high motor control during training. We see that experienced and hardcore users can have increased activity on the alpha and beta over the sensory motor part of the brain. So we can use elements on the training aspect that we can actually just stimulate these areas more on a neurogame, and we can have this type of gamers performing faster and performing better. So this is one aspect that we can include to a neuro game design. And finally, on the other aspect is that since we have a set of electrophysiological and subjective data, we can go towards classifying gamers based on both types of data. So far, there's nothing standardized on doing this job. So having this type of data, and especially extending this type of data pool, we could possibly have a way to classify more correctly gamers and game behavior based on this type of data. And also assess and validate the questionnaires that we've used before. Now, what's next is we need to extend the user base. We need to add more trials, to have more users, to have some concrete statistical significances, and in order to generalize the findings more. Obviously, we need additional electrodes, so we need to get some more cover bigger area on the brain, over the head, especially in the somatosensory area in the center. And finally, to make use of immersive VR environment for training, and to see how experienced gamers can actually perform, again, having an immersive VR environment rather the standardized bar and arrows training as we saw before. Currently, results have been accepted for publication in the Games in Virtual Worlds for Serious Application International Conference, which is an IEEE Computer Society conference, and it's going to be presented this September in Sweden. Thank you very much.